You've probably wondered, how does your bank or your favorite online store or your social media feed manage literally billions of pieces of information without just collapsing into total chaos? Well, the answer comes from a really simple, elegant idea born back in the 1970s that still powers pretty much our entire digital world. So, let's break down the story of the relational model, the concept that quietly brought order to all that data chaos.
And I'm not exaggerating, it really was a maze. See, in the early days of computing, if you wanted to get a single piece of info, you had to know its exact physical path on a disk or a tape. Just imagine telling someone to go get a book, but instead of giving them the title, you give them turn-by-turn directions through the library stacks. Go to the 3rd floor, 5th aisle, 7th shelf, 12th book from the left. You can see the problem, right? One wrong turn, and the whole thing would just fail. So the heart of the issue was something called tight coupling. What that means is the application's code, the actual logic of the program, was completely tangled up with the physical layout of the data. If you needed to change how the data was stored even a tiny bit, guess what? You had to rewrite the entire application. It was fragile, super inefficient, and an absolute nightmare to maintain.
And this really shows you the before and after. The old way was procedural. You had to tell the computer exactly how to navigate that maze, step by step. The relational way, though, it introduced this revolutionary idea, data independence. It's declarative. You just tell the database what you want and it figures out the how all by itself. This separation was the real game changer. It meant you could upgrade your storage or reorganize your data without breaking every single application that touched it. And that's why our digital services are so much more stable and scalable today.
So who do we have to thank for all this? Well, the architect of this revolution was a computer scientist at IBM named Edgar F. Codd. But here's the really amazing part. He didn't find the solution in better engineering or faster hardware. Nope, he found it in the abstract, logical world of pure mathematics.
This quote just says it all. This was his mission. It wasn't just about organizing data a little bit better, it was about liberation. He wanted to free developers from having to worry about where and how every single byte was stored. That way, they could finally focus on what really mattered, the logic of their applications.
So how'd he do it? Well, Codd built his entire model on the foundation of mathematical set theory. And the key was these two dead simple principles. First, in a set, you can't have two identical elements. For a database, that means every single row in a table has to be unique. And second, the order of elements in a set just doesn't matter. And with that one rule, he elegantly just servered the link between the logical data and its physical order on a disk.
All right, to really get this, we've got to learn a little bit of the lingo. There are 3 key terms. First up is relation. Sounds super academic, right? Well, it's just the formal mathematical name for something we all see every day. A table. That's it, a simple table.
Next, each column in that table is called an attribute. Just think of it as a specific property you want to track, like a person's last name, their date of birth, or the price of a product.
And finally, each individual row is called a tuple. A tuple is just one complete entry, one single record in our table, like one specific student or one particular order. So if you put it all together, a relation is just a set of these tuples. Simple as that.
Okay, so theory's cool, vocab is down, but how do we actually go from a blueprint of our data, like a diagram of students and classes, to a concrete set of tables that a computer can actually use? Well, this is where a clear set of rules comes into play.
Let's make this real. Here's a student's table. See that student ID column? We call that the primary key. It's the unique ID for each row, which guarantees that no 2 students are the same. Now look over at the group ID. This little guy is called a foreign key, and this is the magic that connects our data. It's basically a pointer that links a student here to their specific group in a totally separate groups table.
So how do we actually build these links? Well, for the most common type of relationship, the one-to-many, one study group that has many students, it's a simple 3-step recipe. You just take the unique ID from the one side and plant it as a foreign key in the many sides table. That's it. That's the link. But it's not perfect. The model kind of hits a wall with a more complex situation, a many-to-many relationship. Think about it for a second. Many students can enroll in many different courses. How would you represent that using the simple foreign key trick we just saw? The short answer? You can't. The solution, though, is incredibly clever. You create a brand new table that just sits in the middle. It's called a junction table, and its only job is to be a matchmaker, to connect the other two. It would have a student ID column and a course ID column.
And just like that, the one messy, many-to-many relationship gets elegantly broken down into two simple, one-to-many relationships. Problem solved.
Now, creating this structure is one thing, but how do we make sure it stays correct and doesn't fall apart? I mean, what stops someone from adding a student to a group that doesn't even exist? The relational model has built-in guardrails for this, and they're known as integrity constraints.
To keep everything reliable, the relational model basically makes three crucial promises. First is entity integrity, which promises that the primary key can never be empty. Every row has to have a unique ID, period. Second is referential integrity, which protects our links. It guarantees that a foreign key has to point to a real existing record. No more orphan data floating around. And finally, domain integrity makes sure the data itself just makes sense. You can't put text in a number column, for instance.
So, we've seen the power of this model. It's got structure, it's got rules, it's got all these guarantees, but like any powerful tool, it comes with trade-offs. So let's weigh the pros and cons. And the strengths are huge. You've got a simple, unified structure, the freedom of data independence, built-in reliability, and a super powerful language, SQL, to access it all. But this beautiful structure comes at a price, performance, because our data is split across all these different tables. Asking a simple question like, show me all the courses taken by students in Group Alpha, requires the database to stitch all that information back together. And this reassembly process, which is called a join, can be slow and really resource-intensive.
And that brings us to the second big trade-off, complexity. A real-world database for a huge online store isn't 10 tables. It can easily be over 1,000 tables. Just think about that. Navigating that logical web of connections becomes a massive challenge all by itself.
So let's bring it all together. The crucial point here is that this whole model is built on breaking down big, messy information into small, clean, interconnected tables. And this approach is brilliant at solving problems with data duplication and errors. But it leaves us with one final, really critical question.
Just because our data is organized, does that mean it's organized well? How do we know our design is truly efficient and free from all those hidden flaws? Well, the answer lies in a process called normalization. It's a set of rules for structuring our tables to minimize redundancy and really improve data integrity. It's the final step that turns an organized database into a truly robust and elegant one, ensuring Cod's revolution continues to power our world and do it efficiently.